What is image quality and why it's important to have a clear photo? Look at the photos. The one to the left, you can see the detail in that image clearly. You can see the reflection in the water and even the color of the leaves here. But to the right, it's blurred. You can figure out there's a reflection, there is something colorful here, and there is something in the background, but you are not sure about the detail in that image. So high quality image should give you more details. If we enlarge that image, you will see a small dots here. When those dots increase, the quality of the photo will increase too. When those dots are smaller, the quality of image will increase too. The image to the right, you cannot see the dots inside it, which means it contains a really small dot. So small dots, that's immediately a high quality image. Read the details down there. The image to the left contains 300 dots per inch, but the photo to the right contains 72 dots per inch. So when the dots number increase in the photo, that will increase the quality of the photo. Smaller dots, higher quality image. If you watch YouTube, you will see here an option about the quality of the video. You have here 144 pixels in one frame of the video. If you play that video, you can see the frame, but it's blurred. Take a look at the letters here, it isn't that clear. But when you increase the number of those pixels in the frame, you can read it easier now because it's clearer. You can see more details now in easier way. So when the number of the pixels increase in one frame, that means you have higher quality image. Let's reduce it again. Look at the writing here. It's blurred now. So that's what we mean by the quality of the image. When you want to buy any optic system such as camera, for example, or microscope, you need to consider some points to capture a better quality image. Ibn al-Haytham started the idea of the camera when he built a dark room with a small aperture here or a small gap in that room. He noticed that the image of the object outside that dark room will appear inside that closed box. But it was a blur image. Then we discovered the lenses. The basic purpose of the lens of any kind is to collect the light that is scattered by the object and recreate an image of that object in higher quality. But you need to put that lens in the correct place, because if you put that lens in a wrong area, it will give you more blurred image. Optic systems such as camera, microscope, or even your eye depends on this principle and the idea of Ibn al-Haytham. So that's an optical system, which is the camera, the closed dark room. We're using the lens to collect the scattered light coming from the object to form image, a clear image on a sensor. What is the focal length? So we have that lens and we have incident light coming from the object. This positive lens or the convex lens will collect that light in a point which is the focal length. The focal length depends on the power or diameter of that lens. If we have a lens with low power, let's say 2 diopter, the focal length will be longer than lens with higher diopter. So let's say this one is 10 diopter. The focal length here will be shorter than the focal length formed by 2 diopter. So high power immediately means short focal length, and vice versa. When we have a low power, the focal length will become longer. So the idea of the camera or any optical system is to select the right lenses with the right power to collect the light coming from the object in the right focal length. Because if you select a wrong one, for example, a low diopter length, the focal length will be way behind the camera. So your sensor cannot collect that light coming from your object, or you will have a blur image. The same idea occurs inside your eyes. That's the closed room, which is your eyes, and you have the crystalline lens here, and that's your sensor, which is the retina. The crystalline lens will collect the light coming from object and gather it to form an image inside your retina. Your crystalline lens will increase its diameter by increasing its curvature to become something like that, to form an image coming from any object at any distance. Object from here, from here, from here, any distance, by changing the curvature of the lens. That occurs naturally inside your eye. But when you have an optical system such as camera, you need to select the right lens to give you a high quality image. A certain number of parameters must be considered when you choose any optical system. What are those parameters? The first one is the field of view. Let's say that's you. You want to take a selfie for your friend. There are your friends. So the image you will capture will show just those three. What you're going to do is asking your friend to come closer to each other to decrease the size of the frame, or you will go farther. You will put your phone farther to increase the field of view. So the field of view is the total area that can be viewed by the lens, an image onto the camera sensor. If you put your camera near an object, just a small part of that object will appear, just your eyes. But if you put it farther, now the whole face will appear. So the total area that will appear in your phone or your camera, that's the field of the view. The second one is the working distance. Object to lens distance where the image is at its sharpest focus. So again, that's your camera and you want to capture an image for that tree. So in this distance, the tree is not clear in your camera. because that's not the focal length of that lens. What you're going to do is putting your phone here and putting it here again until you have a clear view of your tree. The working distance is the area where should your image become clear and sharp and not blur. We also have the depth of field. Back again to your selfie image. That's what you captured in the selfie. That's your face. And those are your friends, but they are not clear. So you need to change the working distance so all of you will appear clear in your selfie. That's you and those are your friends. And that's the frame. So the depth of field means all this zone and all of the objects inside the photo should appear sharp and focused. So the distance between the closest object, which is you, and farthest objects, which your friend, that appears acceptably sharp in your photo. And of course, we have the sensor size. Of course, inside your camera, such as this one, you need a sensor to receive that image on it. In your eyes, you have your retina as your sensor. Larger sensor size means immediately more pixels inside your frame, which means you will have better quality image. Minimum distance between those dots or your pixels and smaller dots will give you higher resolution, which means immediately higher quality. When the size of those dots increase, that means your frame will have lower amount of the dots and the quality will decrease. Then finally we have the magnification, which is the ratio between the sensor size and field of view. Let's take a look at its image. Longer focal length, such as this one, will give you smaller field of view, and vice versa. With the short focal length, you will have a big field of view. Here you can see the sky, the land, but in a smaller size. And when you increase the focal length, you will just see the house, but also with bigger magnification. Then long focal length will decrease the field of view, but also increase the magnification. In any optic system such as the camera, the image sensor receives incident light or the photons and then focused by the lenses. So lens selection plays a major role in determining image quality or field of view and even depth of field, and other properties of image quality. We have many metrics to measure the image quality of the lenses, such as resolving power, and aberration. So those do need to be considered when you buy a new optical system. Let's start with number 2, the aberration. In an ideal lens, let's say like this convex lens, a positive lens, light from any given point, such as this one,
the spherical
an
aberration.
object pass through the lens and come together at a single point
object
in the image plane. So the distance here should be equal to this
it will
one
focus
here.
in different
But of course,
points,
the lens doesn't
but all those
focus
focus
the light
points
to a single
in the
point
optical
only.
axis.
To have this full
The
image,
ideal image,
the light
the
will focus
focusing
it here,
point
will
should
focus
be
it here,
just
and many
one,
different points to give the
gathering
perfect
the whole
right
light.
image. Sometimes
But as we see
deviations
here in the
happen,
spherical aberration,
which
we
means
have
the focus
many
of the light
points,
occurs in
causing
wrong
the image to
places, such
become
as here,
blur. So
or
let's
here,
say here's
or here,
our image
instead of the
with
ideal
clear detail.
location. And
The
that's
image with
the
spherical
aberration.
aberration will become blur because we don't have a specific focus point. The second one is the chromatic aberration. And from the word chromatic, it's something related to the colors. Chromatic always means colors. In this type of aberration, the different wavelengths of the light will separate, and each one of them will have a different focal point, causing the chromatic aberration. Normally, all the colors should focus at the same point without separation. But here, each one of them has a different focus point. If you look at the image, notice we have at the edges, like here for example, more than one color. We have the yellow, and behind it we have the red color, because each one of them has a different focal point. So the image will be something like that, that the real image should be just a clear cut. But in chromatic aberration, you will see behind the image the different color, red, even green. Sometimes you can see them all, so the image will be with a rainbow next to it. In astigmatism aberration, the rays that lie in perpendicular planes, each one of those will have a different focal point. So let's say that's the normal, and that's our rays, something like this. Normally they should focus here like this. But in astigmatism aberration, they will focus like this. That's the first plane will focus here, and the second plane will focus in totally a different focal point, causing this astigmatism aberration. Take a look at the image and you will see the dots here become long. So mostly with the astigmatism aberration, the resulting image will be elongated. That's the normal image. In astigmatism, it will be something like that, or even in this way, depends on the axis. Coma aberration occurs when parallel rays enter in the lens at a certain angle, but then they will focus at different positions depending on their distance from the optical axis, resulting in comet shape. A comet, guys, means the star with the tail behind it. That's the comet. So the coma aberration gives the same shape. That's the normal image. We will have light behind this formed image. Someone will say, well, it looks like the chromatic aberration. Almost yes, but here with the same color of light. In chromatic aberration, you will see different colors behind the image. But in common, the same white color will cause halos next to the real image. Curvature of field aberration describes the fact that the parallel rays reaching the lens from different directions don't focus on a plane, but it will focus on a curved surface. So see, part focus here, another part here, a third one here, forming a curved image. This causes radial defocusing. So you will see a circular crown only in focus. So the real image will be like this, but in field curvature will be something like that. The edges are blurred, in the middle it's clear. Or the opposite, the peripheral or the edges is clear and blurred in the middle. The last one is the distortion. Distortion mainly means deformity in the dimension of the image. So let's say that's our real image, a full square image without any distortion in its geometric properties. But in distortion, this regular line will have a radial distortion. It will become curved. And we have two types of that radial distortion. The first one is the barrel radial distortion, and we call it barrel because it has the barrel shape with convex edges. Quite the opposite, the concave edges is the pincushion radial distortion. This is the pincushion, which is concave from the edges.
Resolving power is one of the most critical parameters to consider while choosing a lens for your system. And mostly in resolving power, we use something, we call it modulation transfer function. MTF. And MTF literally a quantity measurement for the quality of your lens. And to get MTF, you need to understand two things matter in the image quality, which is the resolution and the contrast. Because MTF determines how much contrast in the original object is maintained by the detector. Contrast means the ability for you to distinguish between the image and the background. Imagine you have image for a human with black hair. To give a good contrast, you need a white background such as this one. So now you easily can differentiate between the hair of the human and the background. But if you have the same image for the same person with same black hair and your background was also black, you cannot differentiate between the background and the hair of your client. So that's an image with low contrast, this one with high contrast. What about the resolution? Resolution means the amount of the detail in your image. For example, if you magnify your image and you still can see the details of your client easily, that's an image with high resolution. But if the image becomes glare with shadows here and there, and you can even see the dots
of your image, that's immediately a low resolution image. Look at the image. Here you can see the white against the gray background. That's a bad contrast or a low contrast. But here you can see the white against the black background, which is the good and high contrast. You can even see clearly the cut or the edge of the white against the background. Here in this edge, you can see a dark gray against the black background. You cannot see the edges of the image, which means in this area you have a bad contrast. Here you have a high contrast, but here you have bad or low contrast. This is the resolution of the image. When you magnify the image and you still can see the details inside the photo, that's a high resolution image. But to the left, there is a dots. You can see the dots or the pixels of the image. That's immediately a low resolution image. As far as you can magnify it and you can see the details without blurring, that's a high quality image. When the pixels, which means those dots, increase, the quality of the image will increase too. In optics, we have something we call it Fourier Lens, and that's immediately the convex positive lens. So any positive lens or any convex lens, that's immediately a Fourier lens. Doesn't matter the power of the lens. Since it's positive, that's immediately a Fourier lens. If we focus lightly by this Fourier lens, and you look from the side, you will see dots. That's the shape from the side, which is dots. If we put a meshwork here in the path of the light, and again you look from the side, the light will be something like that. First of all, the center point of light, here it is, and then the other points will be something like this. So you'll see it from the side like that. If you put a surface here to receive those points, the surface will appear like this. That's the center here. It will be with high intensity. This one will be here, less intensity. And that one here, the least intensity. A little bit of light. If we did the same, but this time with black and white. Let's say we have the barcode that they have it inside the market when you want to buy anything. So the barcode will be lines like that. That's the first one, then line, then another line, then a third or fourth, line, and each one with different size. So how can we read this barcode? Any lens can read this barcode without any problem. That's a good quality lens. Image composed of pixels, one next to the other. High amount of pixels give higher quality image. But also we have something we call it line pair, which is pair of black and white lines next to each other with the same orientation and same width. The ability to differentiate two bars as separated lines in a specific resolution would be based on the contrast level. So, if you had a lens and your lens can differentiate between this bar and this bar without confusion or any aberration, that means this lens has a high quality. But if the image becomes blurred like that, that's immediately a low quality line per millimeter. Extremely useful when comparing lenses. So we can calculate it by line pair or by the pixels. When the size of the pixels decrease, that means we will have high amount of pixels in that picture and the quality will increase too. But if we have a big size pixels, that means we'll have less amount of pixels number in that image, giving a low quality image. The smaller the pixel size, the higher image quality. If we have this image and we saw its pixels, that's the first dot, the pixel, number 1. The other one was white. The third was black, for example. Then we have gray, then again white, and after that a dark gray, then black, a light gray again, and after that let's say we have white again. If I want to transform it into linear shape, that's the white and that's the black. So here we have the black, that's the black here. And then we have the white, here we have the white. We have black again, that's the black, and here we have the white, that's the white. And white again. Then we have gray, something in this area. Then we have the white, a darker shade of gray, then black again, a light gray, and the last one is the white. Then match between them like this. If I turn it into waves or curves, it will be something like that, that the black going to the white, black again, white, this time gray, gray, then white, then a darker gray, then black, then a light gray, and after that the white. It will be something like this. Higher and deeper curves we have in this chart, that immediately we have a high contrast image. To have a good quality image, the black must be truly black and white truly white, with minimal amount of those gray scale between. In MTF, we have a lot of measurement techniques. We can calculate the edge spread function, which means the system responds to a high contrast edge, such as here at the edge you can see the contrast clearly. If it appears like that, that's a low amount of quality. Or also we can use the line spread function, this time measuring the line, not just the edge. Or also we have point spread function, such as this one, when we measured the contrast around those dots. So high contrast in the middle. Here we have lower contrast. Here we have the least contrast. We can look at the image to become clearer. To define the MTF, modulation transfer function, the lens will produce lines with different distances, or we call them the spatial frequency. The more line pairs in millimeter that can be distinguished, the better the resolution of the lens. The ideal lens would produce an image which perfectly matches the object, including all details without any aberration. Here the linear image, and that's the chart of the curve. Highest and deepest curve we have, higher resolution and quality we will have. This area of shading occurs because of the diffraction and interference of the light. All of those parameters, procedures to consider the quality of that lenses, ways to enhance the quality of the image, all of those we call it Fourier optics. Fourier optics is used in the field of optical information processing. And of course, we needed to have an image with higher quality. Eventually, one must always make a compromise between price performance and optic quality. When you have an image, how should you decide it's an image with good quality, bad quality, or even high quality? The more clear details you will have from that image, the better optic system you have. The first thing you need to see in your image is the high transmission and low stray light, which means your lens should succeed in collecting more amount of light and preventing the scattered light. This image is low quality because there is a lot of scattered light. You cannot see details in this area. That's immediately low quality image. Higher image contrast, which means you should differentiate between the image and the background easily. Let me give you another example. In Cruella, the name of this lady, we have high contrast here. You can differentiate between the white hair and the black background. The opposite here, it's low contrast. You cannot differentiate easily between the black hair and the black background. Those are the gray scale. 0 is the black, and here to the right is the white. And between them is the shade of gray ranging from black to white. The scale in the middle will decrease the contrast of the image, but the scale at the edges, such as the white and black, will increase the contrast. For higher quality image, there should be low vignetting, which means the shadows in the image. This one here contains shadow at the edge of the frame, and the one to the left without any shadow. Low geometric distortion should be considered also. Sometimes because the lens is curved, it will cause distortion and changing in the dimension of the image. So this one low quality, this one with high quality. The building here are regular, as you can see it with your bare eyes. Sometimes also we need to use filters to increase the quality of the image. For example, here to the right we use filter to reduce the scatter of the light and also to enhance the quality of the colors. Good quality image should be out of optical imaging errors such as spherical, chromatic aberration, or even stigmatic aberration, because that can affect the dimension and the colors of the image. All the time, the high quality optics must always be adapted to the camera with its image sensor and the intended use. Sometimes we decrease the quality, increase the blur, decrease the contrast just for art causes. But as doctor, as optometrist, we need a higher quality image to be able to read more details from that image.